Chemistry, the Central Science, Chapter 5, Thermochemistry, Lesson 4. Standard enthalpies of formation. So this F here stands for formation, and this not symbol means that we're in standard state. So standard state means that we exist under 1 atmosphere of pressure, because that's typically what barometric pressure is, and 25 degrees Celsius or 298 Kelvin, because that's around room temperature. So around the temperature that most reactions occur in a laboratory. We also talk about standard state in terms of the most stable form of a particular element. So for all elements, standalone metals, right? If I have a chunk of iron, its enthalpy of formation was 0 because it's its elemental form. There was no energy that came about in forming the element. The element existed. That's the way we've defined things, so that then everything else has an enthalpy of formation. So we just said, hey, all elements are going to be 0. Therefore, if I wanted to form ozone from oxygen, I can measure the enthalpy associated with that reaction and figure out that it costs me 142 kilojoules per mole to make ozone, right? This is endothermic. The standard state of carbon is graphite, so that enthalpy of formation is 0. However, if we want to make diamond from graphite, we see that it requires 1.90 kilojoules per mole. So the enthalpies of formation for all things in their elemental form is 0. Every other compound has an enthalpy of formation associated with it. So how do we figure those out? Well, we write out balanced equations showing the formation of 1 mole of a particular compound coming from the elements that make up the compound. So when we're doing this, we have to make sure that we identify the elements, how many we need, and then if we're not sure, we can look in the back of the book at Appendix C to make sure that we're only using the ones that have a 0 enthalpy of formation associated with them. So how can I form chromic acid? Well, I need 2 hydrogens, 2 chromiums, and 4 oxygens. Hydrogen exists as a diatomic molecule. That's a gas. So there's my 2 H's. Chromium is a solid. I need 2 of them, so I put a coefficient here. I need 4 total oxygens. Oxygen exists as a diatomic molecule. So 2 times 2 is 4. I have everything that I need to make 1 mole of this substance. N2O5, I need 2 nitrogens, 5 oxygens. Nitrogen is also a diatomic gas. We have oxygen again as a diatomic gas. I need 5 of them, so I ask myself, what do I multiply by 2 to get to 5? Well, 5 halves. So that allows me to make 1 mole of dinitrogen pentoxide. How about if I want to make iodine heptafluoride as a solid? Well, I need 1 iodine and 7 fluorines. Iodine is a diatomic. It exists as a solid in its elemental form. So 1/2 times 2 is 1. And then since I need 7 fluorines, fluorine is a diatomic gas as well. So 7/2 times 2 gives me 7. And now I've made 1 mole of this compound. So in writing standard enthalpies of formation for particular compounds, the name of the game is what you want to make is your product. You can only have 1 mole of your product. So then you have to balance accordingly on the reactant side to make sure that we have no coefficients on our product side. And we identify that things need to be in their standard state, which means all of these have standard enthalpies of formation of 0 because they're elements. So we can use standard enthalpies of formation to find standard enthalpies of reactions. So RXN stands for reaction. We have our not symbol, which once again means we're standard state. So 25 degrees Celsius, 1 atmosphere of pressure. So looking at a generic balanced equation here, with coefficients being our little letters and our big letters being our compounds, what we look at is taking the sum of the enthalpies of formation of our products, and then we subtract out the sum of the enthalpies of formation of our reactants. And however many we have of our particular substances, so whatever our coefficients are, we multiply those by our enthalpies of formation. So however many you have, it's a number of moles times the enthalpy of formation plus the number of moles times the enthalpy of formation minus the number of moles times the enthalpy of formation plus the number of moles times the enthalpy of formation. So succinctly put, we can use the Greek letter sigma, which means take the sum of, add things up, and then subtract the sum of our reactants added together. So we can look at enthalpies of reactions and determine whether or not something is product or reactant favored. Typically speaking, reactions that are endothermic and require more than 100 kilojoules per mole to occur, we would say that those are reactant favored. Exothermic reactions that are negative 100 kilojoules per mole or greater, meaning more negative, tend to be product favored. So exothermic tends to be favored. Why? Because you don't need any energy. It wants to give off energy. It just kind of wants to happen. But if we take a look here and we look at ice melting to liquid water, right? We know that we need a certain amount of enthalpy, 6.01 kilojoules per mole. We can also think about our circumstances. Is this energy readily available? If it is, then of course ice is going to melt. We just think about what is the temperature. The hotter the temperature it is, the more likely that you're going to melt your ice. You want to keep your ice solid? Well, then you keep it in the freezer, right? But we know if you set your ice cube tray out on the countertop and forget about it, it's going to melt. So if the energy is there, then of course this would favor the products. If it's not there, then it favors the reactants. Over here we have a combustion reaction of methane gas. So this gives off negative 890.4 kilojoules per mole. We would say that this is highly favorable for the products, keeping in mind that, of course, we need an initial spark to start the combustion reaction going. But as long as there is fuel, we know, and oxygen, we know that this is going to give off heat. So let's calculate some enthalpies of reaction from our enthalpies of formation. So we just look in the back of our textbook in Appendix C. You do not have to memorize this table. And so we're going to use our equation that says the sum of the products minus the sum of the reactants. So we first identify what are our products here, how many moles do we have of each, and then we're going to write that down. So before we use any numbers, I like to just write out my equation first so that I can see everything that I need. So 2 times the enthalpy of formation for hydrazine plus 2 times the enthalpy of formation for liquid water. And we want to pay attention to make sure that we're using the right states of matter. Then we're going to subtract out 4 times this enthalpy of formation of ammonia as a gas, and then the enthalpy of formation of oxygen. Well, we know that this is going to be 0 because this is its elemental form. So we do the math, 2 times the value plus 2 times the value, and then we subtract out 4 times this value, and it gives us negative 196.1 kilojoules. So this reaction is exothermic. It is a combustion reaction. We expect combustion reactions to be exothermic. Okay, so now we have our next equation here. Methane plus 4 fluorines gives us carbon tetrafluoride and 4 hydrofluoric acid molecules coming off as a gas. So we have the enthalpy of formation of CF4 plus 4 times the enthalpy of formation of HF, which we've identified here. Then we subtract out our enthalpy of formation for methane as a gas, and then 4 times our enthalpy of formation for fluorine. Well, once again, this is 0 because that's its elemental form. So we do the math. Negative 679.9 kilojoules plus 4 times negative 268.61. Then we subtract a negative, which turns this to a positive value. And we get negative 1,679.5 kilojoules of energy are related to this reaction. So down here, there's a 3 and there's a 4. That 4 shouldn't be there. But anyways, for reaction 3, we see a rearrangement of our nitrogen and oxygen atoms. So we have 4NO2 as our product, and then we have 2N2O4 as our reactant. So we look up our values in the appendix, paying attention to the fact that these are both gases. We do the math, subtract, and get 116.0 kilojoules. So this tells us that this reaction is endothermic. So once again, in terms of favorability, right, we would recognize that these first two reactions favor the products, where this first reaction favors the reactants. So some more practice with enthalpy of reaction. Calcium carbide reacts with water to form acetylene and calcium hydroxide. Using the values listed in Appendix C, calculate the enthalpy of formation for calcium carbide. So we write out a balanced equation, tells us that it reacts with water, so we assume liquid water, and it forms acetylene and calcium hydroxide. Then we go in and we make sure we have a balanced equation. The enthalpy of reaction for this is given to us. It's given as negative 127.2 kilojoules. So this tells me this reaction is exothermic. So once again, I set up my formula before I start plugging values in. So delta H naught reaction equals the enthalpy of formation of calcium hydroxide plus the enthalpy of formation for acetylene. Then we subtract out the enthalpy of formation of calcium carbide plus 2 times the standard enthalpy of formation for liquid water. And we pay attention because water is listed as a solid, a liquid, and a gas. And of course, the enthalpy changes with your state of matter. So now I plug in my values. I know my enthalpy of reaction, so I put that here. I look up my values in the back of the book and write them down accordingly. So now this math is a little different than what we did in the last slide because we were just calculating our enthalpy of reaction. So let's go ahead and combine terms, right? So my enthalpy of negative 986.2 plus 226.77 kilojoules gives me negative 759.2 kilojoules. I'm going to distribute this negative sign. So I'm still subtracting my calcium carbide, and then I'm subtracting a negative value of 571.66, which makes this positive. So if I take negative 75.9.2 plus 571.66, that gives me negative 187.54 kilojoules. Subtracting away still my unknown, what I'm going to solve for. So to get my enthalpy of formation by itself, I'm going to add 187.54 to both sides. So now 60.3 kilojoules equals a negative standard enthalpy of formation of calcium carbide, but we want enthalpies of formation to be positive in terms of the terminology here. So we just switch sides. Basically, we're multiplying everything by -1 or dividing by -1. So now our standard enthalpy of formation of calcium carbide is negative 60.3 kilojoules. To check to make sure that this makes sense, you can always plug it back in up here and see, do I get the same answer? If you do, then you know that you calculated it correctly. So the last thing to talk about in terms of energy is, where do we get our energy from, both for our bodies and for our cars or homes and whatnot? So as far as food goes, we have carbohydrates, fats, and proteins. Your carbohydrates and your proteins give you about the same amount of energy, which is 17 kilojoules per gram. And when you end up with excess carbohydrates, then your body starts to store them as fat. Your fats give you the most amount of energy, which is 38 kilojoules per gram. So even though proteins give you about the same amount of energy as carbohydrates, you don't need your protein in terms of an energy source. You need your proteins for your amino acids so that your body can build everything that you need, like your hair, your fingernails, your hemoglobin, your enzymes. All that stuff comes from your proteins. So fats and carbohydrates are your energy source. It's okay to cut out most of your carbohydrates, but you cannot eliminate all fats because there are essential fats that your body cannot make. And that means that you need to eat them, which is also the same reason why there's 20 essential amino acids, because your body can't make them. You have to eat them. Um, so you can have a diet that's low in carbohydrates and higher in fat and protein. However, your body does need some amount of sugar, and it's more about where are you getting your sugars from. Is it a piece of candy or is it a piece of fruit, right? We know fruit has high sugar content, but you're also getting trace vitamins and minerals and other substances that you wouldn't from just your piece of candy, right? Or your diet, well, I guess not Diet Coke, but your Coca-Cola. So carbohydrates aren't bad for you if you're eating complex carbohydrates. That's the thing that you need to pay attention to. So then as far as the fuels, the energy that we need to drive our cars and light up our homes, so we have non-renewable and renewable sources, right? Non-renewable are your substances that come from, we have to dig them up from the ground, right? Your petroleum, oil, coal, any type of your fossil fuels, natural gas. Um, yeah, so non-renewable means that once we use them, they're gone, right? We cannot get them back. So we want to start thinking about using renewable energy sources instead, like wind farms, solar energy, um, hydroelectric power. So, or you buy a big rushing body of water, then harness the kinetic energy of the water. Geothermal energy is also like, let's just use the thermal energy that is being radiated from underneath the ground. Like, can we use that to heat homes or whatever? So there's a big push and a lot of focus on renewable energy because once again, once this stuff is gone, it's gone. You cannot get it back, right? You burn your coal, it's all carbon based. It turns into carbon dioxide and water. The only way to get that back then is to have plants, right? That then after so many millions of years get compressed, and then you get more coal. So it's important to think about what sources of energy we're using both for our bodies and for our everyday lives.